Okay, enough with materials. Time to actually make with the shading. Well, make with the shaders. As you can see, the objects on screen, these are actually houses. Well, one house that I built in Blender and imported here, and they're using very similar materials. It's just that the shaders are different. So let's have a look at them and see what's going on. So let's start with this one, and it uses Matte Begin. So if I go to Matte Begin, I can see that it's using a custom shader. That's because I built it myself, called Begin Shader. Let's go to Shaders, look at Begin Shader, and see what's happening. I should say, when I say I built it myself, I didn't build it myself. I copied it and changed a couple things from a wonderful resource called Ronya's Tutorials. But it's a really good introduction to what shaders are doing. So shaders are written in a language called HLSL, which stands for High Level Shader Language, because sometimes things are exactly what we name them. HLSL is a high-level shader language. YAML is yet another markup language. Of course, some things aren't what we name them. Python isn't a snake. It's a programming language. And C# won't help your vision. It's a programming language. But back to shaders, let's see what's happening. We have shader and custom begin shader. That's essentially just where we can find it in this list of shaders for our materials. So this, we would find it in standard. There's a whole huge swath of stuff, but custom, whatever. Here are the three that I am using for this project. Then we have properties, underscore color and underscore main text. So this is the color that could be used in our material, and this is the texture that could be used in our material. And they're in properties here because they show up in the editor. Our tint and texture, because we've called this one tint and texture. Now we get to the actual subshader, which this does the calculations for rendering things on screen. So we give it a couple tags, render type equals opaque. That means that it will see it. It won't be transparent. We can do some transparent things, but then we specifically have to say that it is transparent. And Q is geometry. There's a variety of keywords that we can put in here, but Q essentially means it will be rendered at the same time as geometry. We can say it has a far Q or not a far Q, a higher Q or a lower Q, and that's generally the order of things when things will be rendered. So if we have a higher Q, that means it'll be rendered afterwards, which means it will always show up. It won't be blocked out by things that were rendered lower. And there's a couple catches for that. I remember playing Cyberpunk 2077 and had a tree or a couple trees that were always rendered later. And so that means I could see them through buildings and through people, even if they were, halfway across the environment, I could always see these trees, which was very distracting. And I mean, it means that their Q was a little off and they had to fix that in one of their patches. So now we get to actual passes, and you can have more than one pass if you need to, which is quite useful. If you want to outline an object, you can have a pass to render the actual object, and then a second pass underneath it to render the outline. So CG program, CG stands for C for graphics. HLSL sort of took over from CG, but obviously it still uses a lot of the same language. We have pragma here, vertex vert, and pragma, fragment frag. If you remember from database class, what a pragma is it's a directive saying, hey, do this. In databases, we weren't allowed to use rollbacks in triggers. unless you use pragma. If you use pragma, then you could, because it's overriding the normal behavior. So if we didn't have these here, we could have all the functions in the world, but it wouldn't run because we're not telling it to run. So this one, we're saying run this vertex vert and run this fragment frag. So right down here near the bottom, we have vert and we have frag. Here are some variables that we're using. We have main text, and that is the same as up here, which is useful. It means that anything that we have put in the editor here, we can then use during the shader. If we didn't have it here, we could put all sorts of things here, but we wouldn't be able to access them in the shader at all, or the shader wouldn't be able to use them as part of their calculations. We're going to have a main texture underscore st, and then we're going to have fixed for color, and that's the tint that we're using. Next, we're going to create a structure. It's going to have float 4, and that's just 4 floats together. Float 3 would be like a vector, float 2 would be a 2-dimensional vector, and just float is a float that we're all used to. In Java, we tend to use doubles instead. In Unity, we like to default to float. This fixed for color, fixed for you probably haven't seen before. We can get that 4 is 4 fixed together, but what is a fixed? Fixed is a value between 2 and -2, and it is incremented by 256. 1 divided by 256. Which is very useful for colors because they tend to go between 0 and 1, or they tend to go between 0 and 256. It is very useful for colors. It means that we don't have to use float 4s or double 4s, I guess. So it drastically cuts down on the memory that colors take up in our computers. So our structure called appdata is going to take in a vertex that is the position of a vertex. It's also going to take in float to UV texture coordinate. Our textures are in 2 dimensions, so they don't need anything more than that. They need 2 floats, a U coordinate and a V coordinate, and that's generally the conventions around textures is U and V instead of X and Y or X, Y, Z, and W. We also have a structure V2F, and if you're wondering what V2F stands for, it just means vert to frag. It means the output of our vertex can be used as the input for our fragment. And this is also going to take in a float for position, and it's going to be based on the position of our object. And it's again going to take in UV texture coordinate. Now we have the first thing that we're doing, V2F. So we're going to firstly create a V2FO. I imagine that's for object. And its position is going to be Unity object to clip position, which is one of the standard functions that Unity does for us. In fact, Unity does a whole lot for us, and we take great advantage of that so that we don't have to do any of the math ourselves. And it's going to take the vertex of V, so our app data is going to take this vertex here, and then the UV coordinate for the texture is going to be transform texture. It's going to be the UV of this app data here, and then the main texture. So it's essentially mapping the main texture to our V. Then that gets outputted into our fragment right here, SV target. So that's sort of what we want to render. Right now, all we're doing is putting our color on it. So we're going to put the texture or the UV of the eye object, our input. We're going to multiply it by our color. So essentially just the tint that we have. Green or red or purple or orange or yellow or black or white. And then we're just going to return it. So what happens when we run this is we get this object, which is not great. I mean, we can sort of see that it's square-ish, and because I have outlines turned on, we can see kind of where the edges are a bit. But because I'm using a solid color, I can't even see that there is a doorway here. It is exactly the same object as this one. But because our shader is so simple, it doesn't even interact with light.